Welcome back to BrainyBox. You flip a switch and the light turns on instantly. We've always been told that electrons rush through the wires like water, but that simple story hides a mind-bending truth. We picture electrons carrying energy like water through a pipe, dumping their cargo into the bulb and looping back to the battery. It's intuitive, but it's wrong. Electrons aren't delivery trucks hauling energy. The energy doesn't even travel inside the wires. In fact, it's not even in the metal at all. The energy travels through the fields surrounding the wires. While electrons crawl at a snail's pace, the energy zips along at nearly the speed of light. This is the Poynting vector, named after John Henry Poynting. It tells us that whenever you have an electric field and a magnetic field together, energy is flowing. Think of the wires as tracks for a train. They guide the energy, but the cargo is actually in the space between and around those tracks. If you could see these fields, you'd see energy radiating outward from your battery, traveling through the air, and diving into your light bulb from the outside. In an ideal wire with zero resistance, exactly 0% of the power travels inside the metal. It's all in the invisible aura surrounding the circuit. This isn't just theory. Take a coaxial cable, the kind for your internet. The energy doesn't travel through the copper core. It travels through the white plastic insulator. The metal is just there to define the boundaries. This is how high-speed signals stay contained and how your phone chargers work efficiently. On a global scale, massive power lines guide energy across continents using these same invisible fields. It's the most efficient way to move power at scale. This was all discovered in the late 1800s by Maxwell, Heaviside, and Poynting. Yet the simple wrong story is still what most of us learn first. Dismantling this misconception is the first step to seeing the world as a physicist does, not as objects moving, but as fields interacting. From the microchips in your pocket to the grid lighting up your city, the invisible truth of electricity is everywhere. Once you see electricity the right way, you'll never look at a light switch the same again. Thanks for watching BrainyBox. Don't forget to subscribe for more deep dives. Let's do a thought experiment that makes most people's intuition scream in protest. Imagine you have a giant circuit, a battery and a light bulb connected by two extremely long, perfectly conducting wires, each one light-second long, roughly the distance from Earth to the Moon. The wires run parallel to each other, just 1 meter apart, forming a huge rectangle. At one end sits the battery. At the opposite end sits the light bulb. So the bulb is a light second away along the wires, but only 1 meter apart through empty space. Now you close the switch. How long does it take for the bulb to light up? If energy travels with the electrons inside the wires, it would take a very long time. Electrons crawl at roughly the drift speed of a few millimeters per second. It would take years for them to crawl all the way around that enormous loop. In that model, the light would stay dark for decades. But that's not what happens. In reality, the bulb lights up almost immediately. Not in years, not in minutes, not even in seconds. It lights up in roughly 1/c seconds, about 1/300,000th of a second. That's the time it takes for an electromagnetic wave to travel the short 1 meter gap through empty space between the two wires. The electrons in the wire barely move at all in that first instant. The current starts flowing everywhere almost simultaneously. But the energy that actually powers the bulb doesn't travel along the 300,000 kilometer loop. It takes a shortcut. It travels straight through the air or vacuum between the wires. This isn't a trick or a paradox. It's Maxwell's equations in action. The battery creates electric and magnetic fields that spread outward at the speed of light. Those fields interact outside the wires. The energy flows in the space around and between them, not inside the metal. Most of us were taught that a circuit has to be complete. And that's true for steady-state current. But for the initial transient, the moment you close the switch, the energy doesn't care about the long path. It races across the short gap via the fields. This single thought experiment is enough to prove the old model is deeply flawed. If the energy really traveled inside the conductors with the electrons, the bulb couldn't possibly light up so fast. Something else is carrying the power. Something invisible. Something that fills the space around every wire and every circuit you've ever seen. This is how electricity actually works. Physicists call this the Poynting vector. It describes the direction and magnitude of energy flow in electromagnetic fields. This isn't just a curiosity of giant wires. It's happening in your house, your phone, and every power grid on the planet. It forces us to rethink what empty space really is. It's not a void. It's a medium for carrying the energy that powers our world. So next time you flip a switch, remember, the power isn't just in the wires. It's in the space all around them. Thanks for joining me on this journey through the fields. See you in the next experiment. So the bulb lights up almost instantly across that giant 1-meter gap, even though the electrons in the long wires haven't moved more than a hair's breadth. The energy clearly didn't travel inside the conductors. Where is it going? The answer lies in the invisible fields surrounding every current-carrying wire, electric fields and magnetic fields, and in a mathematical arrow called the Poynting vector, discovered by John Henry Poynting in 1884 and independently by Oliver Heaviside around the same time. The Poynting vector S is defined as S, SHU 1 on M0, EX, B. That's the cross product of the electric field E and magnetic field B, scaled by the permeability of free space. The direction of S tells you exactly where electromagnetic energy is flowing, and its magnitude tells you how much power is moving through a given area per second. In a simple DC circuit, battery, wires, bulb, here's what actually happens. Inside the battery, chemical reactions separate charges, creating a strong electric field along the length of the circuit. When you close the switch, that electric field propagates outward at nearly the speed of light, along and around the wires. The current starts flowing, electrons drift slowly, and wherever there's current, there's a magnetic field curling around the wire. Outside the wires, the electric field, pointing roughly from the positive to negative wire, and the magnetic field circling the wires are perpendicular. Their cross product, the Poynting vector, points radially inward, straight toward the surface of the wire and the bulb filament. In other words, the energy flows from the space surrounding the wires into the wires themselves, and then into the resistor, the bulb, where it's converted to heat and light. The fields in the empty space around the circuit are the true carriers of power, not the drifting electrons inside the metal. Think of it like this. The wires aren't pipes full of energy-carrying electrons. They're more like guide rails or waveguides. The electrons provide the mobile charges that sustain the current and shape the fields, but the actual energy is delivered by the electromagnetic field. The Poynting vector arrows form a continuous flow, out from the battery, where chemical energy becomes electromagnetic, along the outside of the wires and directly into the bulb, even taking shortcuts across insulating gaps if the geometry allows. This is why coaxial cables, power lines, and even your USB charger behave the way they do. Most of the energy travels in the fields between conductors or around the cable, not down the copper itself. In high-voltage transmission lines, engineers design spacing and geometry to minimize energy loss in the air, not just to prevent wire heating. The old electrons carry energy story is a useful simplification for DC circuits at low frequencies, but it's fundamentally backwards. The fields do the work. The electrons mostly just shuffle back and forth very slowly, about 0.1 millimeters per second in a typical copper wire. Understanding the Poynting vector is the key to seeing how the universe truly distributes power. Next time you flip a switch, remember, the energy is all around you. Now that we know electrical energy flows through the electromagnetic fields in the space around the wires, not inside them with the slow-moving electrons, a lot of everyday mysteries suddenly make perfect sense. Why can a bird perch on a high-voltage power line without getting fried? If energy traveled inside the wire like water in a pipe, the bird would be in the path of massive current and should be vaporized. But because the energy flows in the fields outside the conductor, the bird sits safely on an equipotential surface. The voltage is the same across its body, so almost no current flows through it. Touch the line and a grounded pole at the same time though, and you complete a path for the fields to push current through you. Game over. The wire is just guiding the fields. The danger lives in the invisible energy flow around it. The same principle explains why your phone charger gets warm even when it's not touching anything hot. The Poynting vector points inward along the entire length of the cable, dumping a tiny fraction of energy into the copper as heat, resistive losses. and the rest into the device at the end. In wireless charging pads, the energy transfer is even more obvious. Alternating magnetic fields from the coil induce currents in the phone's receiver coil, but the power is carried by the oscillating electromagnetic fields through the air gap. No wires needed. This field view also clarifies why coaxial cables and twisted pairs are so good at shielding signals. The return path, outer shield or opposite wire, confines the Poynting vector tightly between conductors, minimizing leakage and interference. In contrast, a simple pair of loose wires radiates more energy outward. That's why high-speed data cables are always shielded or twisted. And here's a fun one. In a superconducting loop with persistent current, zero resistance, electrons drift forever with no energy input. Yet if you try to measure the energy stored in the magnetic field, it's clearly sitting in the space inside the loop, not in the superconductor itself. The Poynting vector still flows, even when there's no voltage drop or dissipation. Understanding this shifts how engineers design things. High-voltage DC transmission lines minimize corona losses, unwanted energy flow into the air as plasma glow, by optimizing bundle geometry to keep fields below breakdown strength. RF engineers think in terms of wave impedance and field containment. Even quantum technologies like superconducting qubits rely on controlling electromagnetic fields in cavities. The energy is stored in the vacuum modes. The big takeaway: electricity is not a flow of charged particles. It's a dance of fields in space. The electrons are essential, but they're more like the medium that shapes the invisible river flowing around them. So we've seen the evidence. The bulb lights up almost instantly across empty space. The Poynting vector carries energy through the fields surrounding the wires, not inside them with the sluggish electrons. This isn't some obscure quantum trick. It's classical electromagnetism, taught correctly for over a century. Yet the old electrons flow like water carrying energy story is still the dominant picture in schools, popular science, and even many technical explanations. Why does the misconception survive? Partly because it's simple and visual. Electrons as little charged marbles rushing around feels intuitive. The real picture: invisible fields crisscrossing space, energy flowing perpendicular to the current, is harder to draw on a whiteboard or explain in 30 seconds. Textbooks and teachers often stick with the simplified model for introductory circuits because it gets students calculating voltage drops and currents quickly. The full field description only becomes essential later, in electromagnetism, transmission lines, antennas, or high-frequency electronics. But keeping the simplification comes at a cost. It hides the profound beauty of Maxwell's equations, that electricity and magnetism are not separate forces, but two sides of one unified electromagnetic field that fills all space. It's a fundamental part of the universe's fabric. When you flip a switch, you're not just closing a loop for electrons, you're launching a ripple in the fabric of space-time itself, a propagating disturbance of E and B fields that delivers energy exactly where it's needed, energy that's already everywhere. That ripple is what powers your home, charges your phone, and lights cities at night. It's the invisible heartbeat of our world. Seeing electricity this way turns every outlet, every power line, every glowing screen into a quiet miracle of field dynamics. The truth also has practical power. Engineers who truly grasp the field view design better antennas and more efficient systems. They reduce interference and optimize energy efficiency in everything from massive data centers to electric vehicles. Understanding field travel helps explain why shielding matters and why high voltage lines need wide spacing to prevent breakdown. At the deepest level, this shift in perspective reminds us how often our intuitions mislead us, and how rewarding deeper understanding can be. The universe isn't a machine of tiny particles shuttling energy. It's a symphony of fields interacting across empty space, guided by precise laws. Thank you for joining me on this journey through BrainyBox. I hope this changed how you look at the world around you. If this made you say, whoa, hit that like button and drop your takeaway in the comments. Subscribe for more reality rewiring science deep dives. What should we explain next? Quantum tunneling in your phone, or the real reason planes fly? Your ideas shape this channel. Until then, keep questioning the ordinary, keep looking closer at the invisible, and stay curious. Remember, the real magic isn't in the wires. It's everywhere around them. See you next time.